Our focus today is on strength of materials in the same stream, which is July, August 2024. That's this paper. So for strength of materials, as usual, just like the other papers we've been looking at, this one is also 8 questions, then you pick any 5. For revision, that's not our concern. We just go through the questions and we leave it there. So right away, let's pick up the first question. Question number 1. So in the first question, what we've been told is we've been given a scenario here where it says we have a steel bar with a rectangular cross-section, meaning we're talking about 3 centimeters by 2 centimeters. Then it's carrying an axial load of 30 kilonewtons. Calculate or estimate the average tensile stress over the normal cross-section of the bar. Now let's pick up the information provided. Number 1, the area of this rectangular cross-section is we multiply those two. Of course, we know that when you have the centimeters, to convert them to meters, you have to divide by 100. So when you divide this first number by 100, you get 0.03. When you divide 2 centimeters by 100, you get 0.02. So that is how come you end up now converting from centimeters to meters, just like that. So once you multiply them together, your answer is 0.0006, and it's already in square meters now. So we are dealing with a shape like that. Of course, pardon my straight lines. Here, 3 centimeters, and there it's 2 centimeters. Now, one thing that is interesting is that we haven't been told, we have not been given the length of this one. I guess it may not be important at the moment, but we haven't been given. So for us, if we want to analyze, we can just say the dimensions are like this, such that perhaps this is our 3 centimeters, this is our 2 centimeters. If we were given the length, we could have now projected it in 3D, and then we tell what that length is, and we include it as well. But as it is, we leave it out. So with this information, that is our area. Apart from that, we've also been provided with the load. We're talking about the force acting on it, which is 30 kilonewtons. 30 kilonewtons means we multiply 30 by 1,000. So that's why you are seeing 30,000 newtons. So we don't leave it in kilo for now. We want it to be converted to the unit, which is easier to relate with. So that's how come we have 30,000 newtons. That's it. Then let's talk about the formula for stress. Stress is force over area. And, oh yeah, I think I forgot, according to the instructions, this one was a compulsory one. We can understand why. That was an interesting one. So stress is force over area. We're saying that the force divided by the area. This force we have is 30,000, and we already have our area there. So our force is 30,000. Our area is 0.0006. So once you do that, you get your stress as 50 million pascals, 50 million newtons per square meter. Oh, if you want, you can express this in megapascals, meaning it will become just 50 megapascals. But my usual advice on that is leave the unit as it is. If you haven't been, look at this question. It has not strained us to provide the answer in a particular SI unit. In a particular unit, is it in kilo, mega? It has just left us to find the final answer. So the answer, the way we found it, we'll leave it like that. No harm done. Here's another one. Now, this question says, we have a tensile test which is carried out on a bar of mild steel, diameter 2 centimeters. The bar at first elongates proportional to the loading before losing its property. It then elongates disproportionately under a load of 80 kilonewtons. It reaches a maximum load of 150 kilonewtons and fails at 70 kilonewtons. Estimate what? Number one, tensile stress at yield point. Thinking about the yield stress, the yield tensile stress. Then the UTS, the ultimate tensile stress. Then also the average stress at breaking point. Now, by the phrasing of the question, one thing you should be able to notice is a pattern. The question has given us a pattern such that you're dealing with a load against extension graph. So if I do this, I draw a load against the extension graph. I draw, this is the load, this is the extension. And what has happened is that when you start at 0, you are moving, it's a straight line. Here, of course, it's just that my hand could be shaky. Then at some point, it reaches a point where it's no longer proportional. Then it continues and it reaches the maximum load at some point, then it breaks. So the maximum load, let me just try to wrap this a bit so that we make it a bit neat. So there. Here we are saying that it loses that proportionality status, does that in many ways, then you have your maximum load, then it eventually fails at some point. So this is the maximum point. This is the point at which the proportional issues are gone. And this is the value at which fails. Now, one thing you can notice is that these are important points. If you look at the load extension graph for mild steel, the one we've put here, this is our yield stress. The material yields, meaning it has been deformed, the proportionality is gone, it's not going to be recovered. Then the maximum value corresponds to this. This is your UTS. Then it ends up snapping at that last point. So with that in mind, we can plot down the data. What is our original cross-sectional area? Our original area requires us to find it using the data as it has been provided. So we're going to use the diameter, the way it is, which is 0.02 squared times pi over 4. Our answer is 3.142 times 10 power negative 4. Yield load, the load at yield point is 80 kilonewtons, which we are converting to 80,000 newtons. The maximum load, which is like our UTS, is 150,000. At failure, the force responsible is 70,000. So that becomes the load at failure. So the first one we're starting with is the tensile stress at yield point. What is the tensile stress when this material is yielding? So go ahead and pick up the formula for that. The formula for the yield stress is simply the force at yield point, or the yield load, divided by the original cross-sectional area. So divide by the original area. So here we've just said yield load over area. Then we substitute. Our yield stress is 80,000 divided by the area we got was 3.142 by 10 power negative 4. So when you enter this in your calculator, what you're supposed to have now is 254,647,908 or 908.947 pascals. The next one is the UTS. By definition, we say that UTS is supposed to be the load or the stress at maximum point. We consider the stress produced by the maximum load experienced by this material as this becomes like our UTS. So we're saying this is the maximum load divided by the original area A. The maximum load we were given was 150,000. What was the area? The area was 3.142 by 10 raised to power negative 4. So with this, just like what we did here, when you're entering this number, cage it, put it in brackets. Otherwise, it will easily misinterpret what you're trying to do. Put this in brackets. You enter the 150,000 divide by, open brackets, you enter what is there, then you close the brackets. So when you do that correctly, you will get here. You're going to find that our UTS is 402,928.071 pascals. Being the UTS means that there's no other stress that is supposed to surpass this one. This is supposed to be the greatest stress, and it's only gotten when you're testing a material to destruction, because only at one point that you'll be able to find this value. So our UTS, therefore, is 477,000 or 1,408,928.071. That is our ultimate tensile stress. In other words, you can say the UTS is 477 megapascals, and you keep it there. But of course, it's nice to write it that way, but you might as well just leave the answer as it is. Part C, what about the average stress at breaking point? The first thing we look at is that when this material is about to fracture, the diameter has reduced to this 1 centimeter. So let's find then the area corresponding to this. Since it's 1 centimeter, it means if you divide the 1 by 100, you get 0.01. So pi times 0.01 squared over 4, you have 7.853 by 10 power negative 5. That is our area when the material is about to fail. Our area at failure. So then what is our average stress then when this is about to fail? So we just go ahead and pick up our load at fracture, divide by the area at failure. What is our area at failure? That's the one we have there. Load 70,000, area 7.853 by 10 power negative 5. And when you try that, you will notice just before it fails, it is 891,267.681.3. This is our average value. Question number 2. State 4 assumptions made when analyzing torsion of thin circular tube and solid circular shaft. So with this, there are quite a number of assumptions. One of them is that we don't expect the material to be changanya. We don't expect the material to be combined with other things. It's supposed to be uniform throughout. It's supposed to be homogeneous. And of course, the shaft or the material we're looking at should be of uniform cross-section over its length. And that torsion we're talking about should be constant along the length of the shaft. Strands before and after the torsion should be asymmetrical without problems. Then applying that, here's our question. It says, determine the torque to be applied to a hollow circular shaft. Diameter 25 millimeters. This is our outside diameter. And 17.5 centimeters inside diameter. Produce a stress of 75 megapascals in the material. Let's arrange our data. Number one, our outer diameter is 25 centimeters. So divide by 100, we have 0.25. Inside diameter is 17.5 centimeters. We do the same, divide by 100. So we have 0.175 meters. Shear stress. The shear stress we've been given as 75 megapascals. So mega represents 10 power 6. Hence, we have 75 times 10 power 6. Polar moment of inertia, J. Because it's a hollow shaft, we have to take care of this part. So we'll say pi over 32, open brackets, the outer diameter power 4 minus the inner diameter power 4. So then pi over 32, open brackets, our outer diameter is 0.25 raised to power 4, minus the inner diameter, which is 0.175, also raised to power 4. So then what happens? Our polar moment of inertia then becomes 2.914 by 10 raised to power negative 4. Then let's apply the torsion equation. From here, T over J is equal to 2 shear stress over D is equal to G theta over L. From the information provided, the last part here is of no use. We're not going to make use of it, so we ignore it. We just pick the first two sets. And from there, we make torque the subject of the formula. So our T is 2 shear stress J over D. And we do the substitution. Our 2 times the shear stress, which is 75 times 10 power 6. J is the one we're just from finding. This is our polar moment of inertia. 2.914 times 10 raised to power negative 4. What about the diameter? The diameter is 0.25. This one, we use the outer diameter. Let me say this again. We always use the outer diameter in this case. If this was a solid shaft, this formula could have easily simplified itself and the J was not even going to appear there. We could have instantly seen the diameters being part of the playing field there. But as it is, we already have the value for J, we just substitute and we are good to go. So what becomes of the torque with such numbers? Our torque is 174,840 Newton meters. This is our torque. Let's proceed to question number 3. In question number 3, we're looking at a scenario of a cantilever. So we're told that we have a cantilever, its length is 4 meters. The UDL has unit 3 kilonewtons per meter. Then it has a vertical load of 2 kilonewtons acting at one free end called A. So then with this loading, we need to calculate, we have to construct the shear force diagram as well as the bending moment diagram. Now, one thing you're going to notice about the shear force and bending moment diagram, about those two, is that you cannot construct them. You cannot draw those diagrams without the numbers, without calculating what the shear forces are. It's like attempting to drive into town, and then you ask someone to blindfold you, then you start driving. How? It means you'll be doing a lot of guesswork. Even if you are a special expert, that will land you into a serious trouble. So the first thing you need to do is to calculate those shear forces as well as the bending moments. After that, we can now do the drawing of each of the two. Now, first things first, the information provided was that the cantilever has a total length of 4 meters. So this is the 4 meters we're seeing here. Then the uniformly distributed load, the UDL acting on it is this 3 kilonewton per meter. Added to that, we were also told that this one, because the cantilever hinged into a wall, as it overhangs, there is a force acting at the far end, at the free end, and that force is 2 kilonewtons, this force we have here. So sketching this, getting from the information provided, this is the setup we have. And the beauty is that the moment you sketch it like that, it will not run out. I mean, it's not going to give you problems because you easily do the calculations. Point B is just next to the wall here. Oh. Whereas A is there. A, B. A, B. Okay, then deliberately I decided to put one point in the middle, which is point K, just to help us have some sanity in the calculations. Let's find then the reactions at RB. There on the wall is going to be an upward reaction pointing up. That's the one we are calling RB. RB. So that's the one we need to calculate. Now, the reason I did this was that practically when you're dealing with a cantilever, you don't even need that reaction. But deliberately, I had to do this because it will help us as we go to make sure that we're on the right track. And that answer is coming out. And we are not going to be guessing as to whether the answer we found is correct or not. That is going to help us counter-check our working. So with that in mind, there we proceed to use the principle of moment, summation. The principle of equilibrium. Summation of upwards forces is equal to summation of downwards forces. Upwards forces, it's just this one. Downwards forces, the first one is 2 kilonewtons. The second one is this UDL covering the length of 4 meters. So meaning we multiply 3 times 4 to get that one. Then we proceed, having that as the case, you can already see that 3 times 4 is 12, and 12 plus 2 gives us a 14. So that is our reaction, our vertical reaction on the wall pointing upwards. Of course, you can go further than that, but for the sake of our drawing, this is enough. We can proceed to the next stage. Shear forces. Now, the shear forces, like I had said deliberately, I had planted this letter K in the middle, trying to tell us that when we are calculating, we take care of A, we take care of K before we go to the last one to make sure that we have more reliable answers. So let's start with point A. One thing you're going to realize, we've always emphasized that whenever you have a combination of a UDL and a point load, always expect 2 values from there. Always expect 2 answers at that point. So suppose this was just a normal loading without this UDL. Then it could have meant that at point A, we practically have nothing. And we put our answer as 0 because we haven't yet moved. There's nothing remaining on the left. So we get back to our scenario. We're dealing with a scenario where we have a point load acting straight on the UDL, and we have that combination. So at this point where we have them, 2 answers, the first answer we have is just this same 0. That is 0. To get the other answer, try to suppose that you've just moved past this negligible distance into there. It means that even the UDL acting there is negligible, but the point load has already remained on the left. What does this even mean? It means that you have, for the same point A, -2 because it's acting downwards and remaining on the left. You have -2 kilonewtons. Let's now go to the mid part. This part here in the middle, that's point K. In the case of point K, you have, first of all, these 2 kilonewtons, -2 kilonewtons acting downwards. Then we also have another stream acting downwards. So we say -3 multiplied by the distance from here up to there, this one. Now, since the total length of this span is actually 4, it means half of 4 gives us 2. Hence, 3 times 2. So 3 times 2 gives us a 6, and this is a -2. -2 minus 6. -2 minus 6, you get -8. And remember, this is a shear what? Shear force. So it should be able to carry the unit for a force. So this product gives us a 6, whereas on the other end, we already have a -2. So -2 minus the 6, that is what leads us here. The next part is when now we go to the wall and we say, at point B, what is my shear force? So at point B, it means all these things remain on the left. So what I have now is the force acting downwards, which is -2, minus the same one, which is -3, times this time around the total distance. -3 times what is our total distance? In this case, our total distance is 4 meters. So hence, we have -2 minus 3 times 4. We already know that if you say 3 times 4, you get a 12. So -2 minus 12 is supposed to give us our -14. And that is our answer for this part. Let me just remove this. We just remain with the essentials. Okay, so this is in fact, this one was not supposed to go. We are saying our point B is here. Okay. Now remember what I said earlier. We got the reaction. At this stage, you can verify that the answer we found is a reaction. Meaning that if someone had started calculating from the wall coming inside, they should be able to reproduce all these answers. Except they will start with the last answer and end up with what we got as our first answer. But the values will be respected. Even when you decide to draw, the kind of graph that you're going to draw will just be the same as what we've done here. So our shear force at point F, is it even point F? Rather, point B is -14 kilonewtons. Let's go to the bending moments. What you find interesting about bending moments is that they respect the distances. These ones, the distances are critical. So it becomes even easier to maneuver. So bending moments, I'll start with point A. At point A, I have -2 times how much distance am I leaving on the left? There's nothing. So -2 times that same neo, which is 0. -2 times 0 gives me the same 0 there. Let's come to the midpoint. This is now point K. In the case of point K, you can see we're saying the moment is equal to, I have -2 multiplied by this distance from here up to where K is. So -2 times 2, because that's halfway. Then what about the last part? I mean, the other part, which is the UDL. The UDL that we're dealing with is just this one from the center to there, which is covering 2 meters. Even this part, when you consider this part, The force as a result of the UDL, just like any uniform material, is acting at the center here. How do we even do that? We can do it smartly. So to get the force, we multiply 3 by the 2 because we know from here to the far end it's 2. Then multiplied by this distance, divide by 2. We have 2 divided by 2. Then we have our span. And once you do that, our answer comes out as negative 10 kilonewton meters. Let's pick up the last one. At point B, we're saying that our moment is equal to, first, if you look at negative 2 has now the increased span, which is coming up to here. Talking about negative 4. So negative 2 times 4 minus, this is 3. So we're saying 3 times the whole 4 multiplied by, this will now act at the center, multiplied by 4 over 2, which is basically the same 2 from here to there. So we're saying the first part is negative 2 times the whole distance, which is 4, followed by the UDL. Our UDL is negative 3 times 4, because it's using the whole distance, which is 4 meters, where the UDL is acting. Then times the distance from where the UDL is acting up to where we are. The UDL is acting at the center of this, which is at point K, up to there. So what you will notice again, here we said from A to K, you got 2 meters. And at the same time, moving from K to this side, you get yet another 2 meters. So what are we talking about? We're saying just get the whole 4 and divide it by 2. Then you multiply by this. So this has given you the span, the length that you are dealing with at this point. So like that, the question was asking us to draw the shear force diagram as well as the bending moment diagram. So meaning that the top part is representing part A. This is representing part A. Then this other one is representing part B. Then, having done that, then we are saying that let's plug the numbers as they were. For the shear force, we said we had 2 values. We had 0 and negative 2. Everything in kilonewtons. Next, because up here on top, this is positive, below there is negative. So hence we've measured the 2 going downwards. When we come to point K is here and we're told it's 8 kilonewtons. So we've marked out the 8. The last one is 14, which is close to half what we had. So negative 14 is our answer on the far end. So what do we do with it? We're now going to say, we've marked it there. After that, those points we marked, we just connect them with a straight line. And then there's an enclosure. So here, and also going this other side and there. This is our shear force diagram. And it's not mandatory to shade, like I keep saying. This is something you decide on your own. Next, what about the bending moment? According to the bending moment, at point A, we had 0. At point B, negative 10. So we mark out negative 10. At point C, we have negative 30. So negative 30 is in the negative region. Like we said, Dokumuru is the positive, Unshkula is the negative. Then this axis is just there at the center. So once you mark them out, you do the same from point O there. You join those points with a very good line. Unfortunately, this time, the line is no longer straight, it's parabolic, it's a curve. Just like as you saw for the shear force, the line was looking like it's now for a bending moment because it was at an angle. With this one, the line goes like that as a curve. Again, if you want, you can feel free to shade. Okay, so that is our bending moment and shear force diagram. The first thing you can see is that we had to redraw this graph, this diagram the way it was. Then, of course, we cannot label all the properties provided. Sometimes they will have a way of dealing with them. So after you copy the question the way it was, the diagram, then below it, you can now start planting your shear force and also the bending moment below it once all has been gathered together. Now here's our next question. We were told that given that the maximum bending moment is 4 kilonewton meters, determine what? Position of XX, this is the neutral axis. Moment of inertia about the neutral axis, which is XX. Then maximum bending stress. So having done that, we didn't even put up the data because that will be taken care of by the table. So we go, we proceed. Here's our table. We have the top flange, which is in this section 1. The top flange has dimensions 100 by 40. This is 40 as picked from here. Then this one is 100. And hence, to get the area, we multiply that 40 by 100 and we get 4,000, which in square meters, it's 0.004 square meters. Then we proceed now, the web A2. What we are calling web is this thing in the middle here, which is connecting the two. This is our 2. Okay, so what are we going to do? For area 2, you can already see that the length here is 100. But the width, the cross section on the other end for the same material has been given here as 40 millimeters. So we multiply 100 by 40 because this is 100, then 40 is across. Again, our answer is 4,000 square millimeters. If you convert to square meters, it's 0.004 meters squared, giving us the same value for the centroid is 50 plus 50. You have 100 millimeters. The next, we also have now the third one, which is the bottom flange, because this one is number 2. Then this one, number 3, is at the base there as a brand, or rather 3 as a unit on its own. So what are we going to do? We're going to multiply this length by the width, meaning 120 times 50. And we get 6,000, which is 0.006. Okay. Now, having done this, the next thing you can do is sum them up. 4,000 plus 4,000 plus 6,000. The end result is you have 14,000. Then let's proceed now to the moments, where we will multiply the base area by all we are going to do is to locate the centroid for each of the 3 shapes, starting with the top one, then going down. So like, for example, let me sample the first one. Just erase this. Okay, so what we get when you add these 14,000? Next, we're saying we are picking, let me just get a pen also. This is where we are measuring our centroid from, then going up. So the topmost, the center of this top shape, the centroid for this shape is at its center because it hasn't been damaged. So here, from the top up to here, that distance you see there. So then what we have is this distance from here going up. You can already see that the distance from here up to here is 150. But the distance moving from here to this is supposed to be half of the 40, which is 20. So what is 150 plus the 20? So for me, that's why I just broke it down. We have 50 plus the 100 plus the 20. So in the end, the result is 170. So 170. Then let's do the same for the next one. The web in the middle, section 2, this one. With this one, the center of 100 is a 50. The center for this one is a 50. So meaning that moving from the base to the centroid for this one, we'll do this. And we will add, this is 50 plus, the other one we've just found is 50. 50 plus 50 gives us the centroid for the mid web. And that's our 100. The last one is this one here. Its center is also here at the center, just like that. To find the center for this one, we just get the provided parameter, the 50, and divide it by 2. So that's the 50 divided by 2. You end up with your 25. It's already labeled. The units are millimeters. The next thing you do is do a combination. You multiply the area by this value found, the area by the centroid, the area by the centroid. So the area is 4,000 multiplied by 170. So 4,000 times 170. This is our area times by y. First one gives us 680,000. The next one, we're saying 4,000 times 100, giving us 400,000. Next is 25 times 6,000. 25, rather 25 years multiplied by 6,000. So our result is 150,000. So just like what we did with the areas, we're going to do the same here. We add all these together. You have 1,230,000. Now, 1,230,000, the unit it's using is cubic millimeters. And it has already now arrived. It has given us the answer we're looking for. This is the summation of area times by y. We will divide it by the area. Ideally, if you see the way they behave, if this was to cancel out, you have what is on the left. So hence, we are justified to use this because we're not changing anything. We're just trying to make our life easier. Now, let's do the substitution. Just let me remove this. Okay, so we have, just pick a pen again. Summation of area times by y came out as 1,230,000. Then the summation of the area is actually 14,000. So what do you get? 87.857. If you convert it to meters, it becomes 0.087857. But then this is the centroid, and we have our answer. Now, for the sake of making your work easy, I added something else to help us deal with the next part. The centroid from the top, because what we have found is from there, from the x-axis going there. What if we could attempt to solve this, then coming down to Cornelius, or rather coming down to the center here? So then with this, it means we will have two values, and all we do is the answer that we found, subtract the total value of all these things you see here. So that's how come we're saying 190, which is the total. 40 plus 100 is 140 plus 50. That's the 190. Minus the value for the centroid from the base, which is 87.857. And your result is 102.143, which is 0.1021, 0.102143 meters. What is the moment of inertia about AXX? So we add the moment of inertia for the first shape plus the moment of inertia for the second one plus the third one. Now what we are doing is to get BD cubed over the value first of all, the standard way of calculating this one by 12. Then we add the product area times by y squared. Now, the beauty is that all the three are rectangular in shape. So we use BD cubed over 12 plus area 1 times by y1. We repeat this up to 0.3. So let's start with the first one. B is 0.1, D is 0.04, cubed by 12, plus, then we have this one, which is A1, area 1 is 0.04, times Z by Y1. But Y1 is the distance between the centroid for this shape and the overall centroid. So 1021 minus 0.02, and we square it. We repeat the same for the next one, which is again 0.04. This is for the midway, 0.04 times 0.1 cubed over 12 plus 0.004. Then this time around it's 0.1 minus 0.087857, and we square the result. The last one, we do not have a lot of drama. We're saying 0.12 times 0.05 cubed over 12 plus, outside the bracket, we have 0.006. Then open brackets, we get the difference between 10,087,857 minus 0.025. You square that result. When you enter this in your calculator, you should be able to find 0.00005578, because this is in now meter power 4. So that's how you find the centroid for such a shape. What about the maximum bending stress? With the maximum bending stress, we go back to this expression where we're saying shear stress over Y is equal to M over I. And we just do the substitution or make it the subject of the formula. We have My over I is equal to the same stress. And M is 4,000. Our Y, considering what we got, is 0.087857. Then I is 0.00005578. And as a result, our tensile bending stress becomes 6,300,250.986. Now, this is on the lower side. What about the upper side? You use the other value of the centroid, where we measured it from the top coming to the centroid, which is the one that gave us 1021. So 4,000 times 1021 over 0.00005578. So with this, you get our stress, the compressive stress of 731,620.652. So this is how they stand out. And of course, you can already see that the effect for the compressive one is higher, and it's the one we can even pick for the maximum bending stress without affecting anything. But for now, these have to be side by side before you make a conclusion, because you have a comparison why you have taken up an action, why perhaps you delayed seeing this, and all that. So tensile stress 6.3, the other one is 7 million. So we can even leave this the way it is and we move. Question number 5. So it's asking us to explain the following terms applied to stress analysis: volumetric strain, bulk modulus, principal stress. Volumetric strain, we're saying that this is the ratio between the change in volume over the original volume. Then bulk modulus, the measure of its resistance or material's resistance to compression or expansion when external pressure is acting on it. Then what about the principal stresses? The principal stresses, there are normally 3. You can have stress 1, stress 2, stress 3, and they refer to the direct stress. So you have the mostly like that. You have the maximum, minimum, or we're saying either minimum or maximum normal stress acting on a material at any given point. So you can have stress number 1, 2, or 3, where 1 is the maximum one, 2 the mid, and 3 usually that's the compressive one. So we have the principal tensile stresses induced at a point across 2 perpendicular planes in a material at 75 megapascals and 35 megapascals. Determine the normal tangential and resultant stresses induced in the material and the obliquity of the resultant on a plane at 20 degrees to the major principal axis. Data, information provided. First, stress in the x-axis. Tensile stress is positive 75 megapascals. Stress in the y-axis, 35 megapascals. Then we also have the angle of obliquity before anything, before the action. So theta, 20 degrees. So under normal circumstances, we're supposed to say the normal stress is equal to stress x plus stress y over 2, which is like the average, plus stress x minus stress y over 2. Then we introduce the theta. And this changes depending on what you're dealing with, or the shape of what you're dealing with, or any other factors that could be provided. So here's our normal stress. We can do the substitution. Our stress x is 75, stress y is 35, and we divide both of them by 2. Then plus stress x 75 minus 35, everything over 2, multiplied by cos 2 theta, meaning cos 2 times 20, referring now to cos 40. The result from all this is 70.321 megapascals. Okay, so those, next is the tangential shear stress. It's also part of this, which is stress x minus stress y over 2, then sine 2 theta. So then we have 75 minus 35 over 2 multiplied by sine 2 times 20, giving us a sine 40. Our result is 12.856 megapascals. So this one, we've already done the conversion because the other values were already in some unit, which is easy to get to this. The resultant stress now comes in to combine the two. The direct stress squared plus, or rather the normal stress squared plus the shear stress squared, everything under the root. This is supposed to give us now the resultant stress. So the resultant stress, we substitute. The normal shear stress is 70.321 square it plus The actual shear stress is 20.856. Next, our answer is 71.487. 71.487. What about the obliquity of the resultant? Basically, we're just asking for the angle. So the angle, to find it, we use tan phi is equal to shear stress over the normal stress. So then to get our phi, we say tan inverse of that value, which is shear stress over the normal stress. Then phi is tan inverse of the shear stress was 12.856 over the normal stress was 70.321. So with this, our angle is 10.36. That's our obliquity, or the angle of obliquity, considering that this is what we've gotten from the value. Here's question number 6. State 8 advantages of welded joints. You can even go up to 10 or 20, but otherwise, for the sake of this one, just sample 8. We're saying that such joints are welded better, they are more efficient, they are also stronger and reliable. They equally last long, so we can say they are durable and even effective. Then it is easier to correct mistakes in the process. Just introduce heat and you're good to go. Meaning that when you're working, you find that you've just made a mistake, you can easily dismantle, remove the weld, and then make your corrections, and you still have a very perfectly well-rounded joint. The pieces will be joined together smoothly. The other thing about this is that the surface finish when you do welding is brilliant. It usually looks attractive, especially you use a coated welder, a specialist. So all those are the advantages. And I keep emphasizing even over here that when it comes to remembering things, do not think that it's supposed to be done perhaps in a special way. The more you practice, the more these remain on your fingertips. Immediately done, we've talked about this. So the next one is describe fusion welding, then there's forge welding. So in fusion welding, you're melting two parts together such that when they solidify, as long as they're in contact, a joint will be formed. Then what about forge welding? Forge welding, this is a very special kind of welding process which is used by blacksmiths. So this is the welding process that involves heating the two metal pieces at high temperatures. And then later on, you can start the hammering and processing, making sure that it retains the shape that you're looking for. And should there be any induced stresses, the trapped ones, it's very easy now to deal with them at this point. So forging, those processes being now done after you've heated the material. Okay, so here we have a steel strip, 5 centimeter wide, is fillet welded to a steel plate over a length of 7.5 centimeters across the end of the strip. So the tensile load carried by this is 100 kilonewtons, and the longitudinal stress is 70 megapascals. Then the other one, which is like the transverse one, is 100. Let's start by looking at the length of the transverse weld. What we are calling a transverse weld is this one here. Then the longitudinal one is along the length of the weld, so it's this one, talking about that, all the way to the end there. So there are two, because there's one here on top and another one below. So area of the thought, area of this is supposed to be 0.05 legs and 45. Why 0.05? Because this is the one we have here. This is for transverse. There, as 5 centimeters. And if you talk about the longitudinal one, along the length, you can already see that this is the length 7.5 meters, and there are two. So 7.5 centimeters divided by 100, you get 0.075. At the same time, you have two of them. So then your length for the longitudinal world becomes 0.15 meters. But we are targeting the area for this. So it becomes a minute. Area of the longitudinal stresses, we're talking about the throat area, which is responsible for actively trying to keep this joint straight, trying to keep this joint strong enough to hold the pieces joined together. So we have length times the throat. So we're saying 0.15, which came out as the length of the longitudinal thread, multiplied by the thickness, which is leg sine theta. What we are calling leg is basically the weld size. So what are we going to do? We pick up the next step. We're saying the transverse fillets, they are under a stress of 100 million pascals. What about the longitudinal fillets? They are under a stress of 75 million, or 75 by 10 power 6 pascals. So that is for the tensile stress. Then what about the total force on the weld? It means we'll have to add, but otherwise for now, we have the force acting on the weld is just one, and that's the one you can see there as 100,000. Now here we're saying that the total load is supposed to be equal to the load carried by the transverse fillet plus the load carried by the longitudinal fillets. Then the only thing we can say is that when you talk about the load carried by the transverse fillets, then you're talking about the longitudinal load or the longitudinal type on that end. So let's talk about now how much load is this longitudinal thread carrying. We multiply the stress in the transverse stress by the transverse area. For the transverse stress, take it back to our data. It's here, 100 by 10 power 6. So 100 by 10 power 6 times the area, which is 0.05, multiplied by leg sine 45. Then FT, meaning we end up now with 5 million leg sine 45. Then what about the load carried by the other ones, the longitudinal fillets? It will be area times the length, meaning 76 million times 0.15 times leg sine 45. Okay, so we have load carried by the longitudinal fillets, where we've said that, okay, we say area of the longitudinal fillet by the stress of the longitudinal fillet. So we have 75 by 10 power 6 multiplied by this one, which is 0.15 by leg sine 45. So here we had 5 million, but with this one, we end up with 11,250,000 by leg sine 45. Then we can now talk about the total load carried by these welds. So we add the two values, which is FT plus FL. So FT plus FL. So we're saying that the total force F is supposed to be equal to the load carried by each one separately. So 100,000 is equal to 5 million leg sine 45 plus 11,250,000 leg sine 45. Our target is to make leg the subject, so we can factorize it. Everything remains in the brackets. So once you get your value, you find that your answer for the leg is taken as 8.703 by 10 raised to power negative 3. Where would you find such a welding rod in case you have to? So we take 9 millimeters as the size. Question 7, finally. Explain these terms. A strut, we're saying that a strut is supposed to be a member which is loaded in compression. Rather, can even call it a member carrying a compressive load. Then a column is basically a long strut, meaning you stand it erect, it is erected above the ground, it has some considerable length, and that makes a column. How do we distinguish between a long and a short column? In a short column, the cross section is normally not big enough compared to the length is almost smaller than the cross section. They compete. But with a long strut, with a long column, you will find that the length is much bigger than the cross section. Then that column is long. So that's what this is addressing. Yeah. Now here's our question. We have a hollow alloy 5,000 millimeters long with external and internal diameter of 50 millimeters and 25 millimeters respectively, used as a column with one end fixed and the other end hinged. Determine the buckling load for Euler formula, taking E as 180 gigapascals. Data as usual, first stopover. Our length is 5,000 millimeters, which is 5 meters. Diameter is 50 millimeters. When you divide that by 1,000, you get 0.05. Then the small diameter, the internal diameter is 25, meaning 0.025. Then we have Young's modulus. The giga represents 10 power 9. So we're saying 180 times 10 power 9. Now, the end is fixed and the other end is hinged. With such a condition, we talk about the equivalent length, which is L over root 2. So then, since we know that our length was 5 meters, so 5 over root 2, and we get 3.536 meters as our equivalent length. Then the next thing we calculate is the moment of inertia. The moment of inertia for this hollow, the hollow member. So we say pi outer diameter power 4 minus inner diameter power 4, everything divided by 64. So pi times 0.05 raised to power 4 minus 0.025 raised to power 4 divided by 64. Our answer, 2.876 by 10⁻⁻7. This is in quadrometers, so meter raised to power 4. Then we now apply Euler load. Euler load is pi squared EI over equivalent length. So once we substitute, we have pi squared multiplied by 180 multiplied by 10 power 9 multiplied by 2.876 times 10 raised to power -7 divided by LE squared, which is 3.536 squared. And our answer is 40,863.6. That is how you handle the Euler load. So for now, we'll end here. Look out for the next one, because we're going to explore yet another different paper for your revision.